Hi, my name is Rich Pauloo, and before I begin, I want to thank the conveners of the session for having me. This talk is about how geologic heterogeneity and hydraulic gradients interact to influence non-Fickian transport in regional scale alluvial aquifer systems. The fundamental questions we seek to answer are captured here in these 2 points. Number one, how do changes in mean flow directions, such as those caused by oscillating patterns of pumping and recharge, impact non-Fickian transport of contaminant plumes? And secondly, how does 3D geologic heterogeneity interact with changes in the mean flow direction to influence that non-Fickian transport? This project's motivated by the need for upscaled transport models to address challenges to alluvial aquifer quality sustainability, such as those posed by regional scale non-point source contamination from nitrates and fertilizers and pesticides. And it's also motivated by the fact that upscaled transport models fail to reproduce tailing observed when the mean flow direction changes, as demonstrated in these studies. We lack this understanding, likely because most studies investigate relatively simple unidirectional flow. However, flow directions can significantly change in regional aquifers, which is what we seek to model here. A quick note, I use anomalous and non-Fickian interchangeably. They mean the same thing. Transport's anomalous when it can't be described by these laws, fixed laws of diffusion, which basically say that the diffusion goes from high concentration to low concentration proportional to the concentration gradient. For example, consider this homogeneous isotropic aquifer. We have an instantaneous point source injection, uniform flow from left to right, and the plume is stretched along the longitudinal direction. There's transverse diffusive scaling as well. This is nice and predictable Fickian transport. But homogeneous isotropic aquifers don't exist in nature. They look more like this in the figure below, which is an example of some higher K layers interspersed by some fines, where we see fingering and preferential flow of the plume along these high K layers and mass holdback near the source. And this is more non-Fickian transport. Key features of non-Fickian transport include tailing, early arrival, and nonlinear scaling of the second spatial moment. So if you were to measure the concentration of an arriving solute at some control plane, in a Fickian world, the breakthrough of that contaminant would look very Gaussian, this red line here in the first plot. But and that works really well for homogeneous media, but the real world's not homogeneous. The breakthrough curves for transport in heterogeneous media would look more like this blue line. There'd be tailing, which is this long, heavy tail representing mass transport, slower to arrive than we'd expect given fixed law, and also early mass arrival. We can also calculate the mean squared displacement of the plume, or the plume spatial variance, how much it's spreading out, which in a Fickian process would be linear with respect to time, or a slope of phi equal to 1. And deviations from this scaling would have phi less than 1 or greater than 1, indicating slower or faster than Fickian diffusive scaling. And we call these subdiffusion and superdiffusion respectively. Spatial heterogeneity that imparts heterogeneity onto the velocity field and then hence the transport. This is ubiquitous across all geologic media and all types, from fractures to porous rock, and across spatial scales. So I study transport at this regional scale here. And in order to model these regional scale processes, we need an understanding of the regional geology. In my study site of California's Central Valley, the aquifers are created by evolving rivers that drain the Sierra and Coast Range watersheds over geologic timescales. Alluvial fans deposited correlating, interconnecting high K channel networks interspersed by low K fine grain floodplain deposits. So this is not a homogeneous isotropic aquifer, nor it's a layered system, but it's rather this 3D connected network with preferential pathways interspersed with immobile stagnation zones. Here's that model, 3D model domain that we use, split by facies. The model was developed using the transition probability geostatistics approach by Weissman et al. And represents the Kings River fan in California Central Valley. I'll show that in the next slide in more detail. There were 4 sequences created during Pleistocene glacial cycles, each of them separated by laterally extensive paleosols, which formed during the interglacial periods of pedogenesis. And these are very low conductivity and act as aquitards, but they also have windows between them that facilitate transport. I'll also have highlighted the main section of this incised valley fill, a paleo channel of gravel and sands, and a side view of the laterally extensive and thin paleosols. So here's the main figure of the model. There's a lot going on here, so I'll explain it. There's a cutaway to show what's inside of the model, and the location of the model is shown by this blue box in this map here. I've also highlighted 4 representative particle trajectories corresponding to the 4 mean flow directions we test in this study. And remember, we want to see what happens to non-Fickian transport as you go from mostly horizontal flow to mostly vertical flow. And we do that by modulating the vertical gradient. So we keep the horizontal gradient constant, and then we dial up or down the vertical gradient. So we call that the vertical to horizontal gradient ratio, or VHGR. And I'll be using that throughout the rest of this talk. So a VHGR of 1 means equal horizontal and vertical gradient. A VHGR of 0.1 means mostly horizontal flow, and then conversely, greater than 1 is mostly vertical flow. And note that these vectors are not to scale. Also, we inject the non-point source plume 10 meters below the land surface, indicated by this pink line here. Here are our methods. We solve the 3D steady state groundwater flow equation in ModFlow with constant head boundary conditions on the top, bottom, down gradient, up gradient faces to maintain uniform diagonal flow, and no flow boundary conditions on the sides. And we solve particle transport via the random walk method with the code RW3D. And we change the mean flow direction by increasing the VHGR, which is the ratio of vertical to horizontal gradients. And so higher VHGR means more vertical flow. Calculating the hydrofacies level Peclet number is actually quite informative. Remember, Peclet number is the ratio of advective to diffusive flux. So PE greater than 1 means the system's advection dominant, and less than 1 means it's diffusion dominant. But we actually have 5 hydrofacies that each have their own Peclet number all in one system, and they're all interacting. So this table shows that. And the takeaway here is that under a more natural ambient horizontal gradient, say VHGR equal to 1, low K facies like mud and paleosols are diffusion dominant and hold back mass. But when pumping and recharge increase the vertical flow, these facies actually become advection dominant, they transition. And as that transition takes place, there is a consequence on how non-Fickian the transport becomes, because these once diffusion dominant facies are now advection dominants. So as in the case of VHGR equals 100. So we should see some evidence of that in our metrics of non-Fickian transport, which include tailing, plume spatial variance, and the final particle position and residence time distribution, which that's how I'll introduce the results in the next couple of slides. So first, for tailing, we fit a T-fade model to the breakthrough curves. It's one of many clever ways to upscale the ADE, advection dispersion equation. And importantly, there's parameter lambda that represents how mass moves from immobile to mobile zones, and a smaller lambda means more tailing. So we're going to look at that, and then we're also going to look at the slope of the breakthrough curves themselves. Then we're going to measure the plume spatial variance with the MSD, or the mean squared displacement. This is like how stretched out it is in space. And lastly, we look at the final particle positions for evidence of preferential flow. So here are the transport simulations and what they look like. I've made most of the domain transparent, and notice that non-point source injection plane, that was that pink plane in other figures. As the VHGR decreases, the plume gets more spread out along the longitudinal direction. And we can also see some spots on the front face where you get more preferential flow as the flow is more horizontal. And I'll show later how those correspond to sand and gravel bodies. Onto the tailing, we measure tailing at a control plane at the bottom of the model. This is the pink plane in this figure at the bottom here. And figures A through D are the breakthrough curves for the VHGR scenarios. The colored points are what we get from particle tracking, RW3D, and the black line are the T-fade, is the fitted T-fade model. And remember that truncation parameter lambda, the results are shown in this table here, and going from VHGR 100 to 1, going from mostly vertical to horizontal flow, the truncation parameter decreases by by about 2 orders of magnitude. And so this is confirmed also just by looking at the slopes of the breakthrough curves in a log-log plot. We can see that the slope becomes more positive, indicating more tailing as you go from mostly vertical flow to mostly horizontal flow. Now looking at the plume spatial variance, on the y-axis is the MSD, the mean squared displacement. I'm only showing the longitudinal direction. In the paper, we have all directions we analyze. And recall the MSD slope equal to 1 means Fickian scaling. In the longitudinal direction, we see the magnitude of the longitudinal MSD increases as flow is more horizontal. So as you go from pink to green, the actual magnitude, the spatial variance is much bigger. And as flow is more horizontal, early time scaling is more super diffusive, and the late time scaling starts to slow and become less super diffusive, but it remains persistently pre-asymptotic, meaning that it doesn't transition to a slope of 1. And this is consistent with what we observe in other heterogeneous systems. So persistently pre-asymptotic scaling is not a new concept. It suggests rather that the transition from anomalous early time scaling to late time Fickian transport may never occur in natural geologic formations under certain hydraulic conditions. However, why does Fickian scaling take place when flow is mostly vertical? Looking at this pink line, that's pretty close to a slope of 1 early and late time. So the intuition behind this is that at high VHGR, this pink line, all the facies are advection dominant. Recall those high Peclet numbers. And so the particles are forced downward through all the facies, generating this ergodic sample of the system heterogeneity. By contrast, as the flow is more horizontal, diffusion dominant facies can hold mass back, and preferential flow paths can advance the leading edge of the plume, contributing to the larger spatial variance, but also the stretching of that plume, encountering more heterogeneity before the Fickian scalings ever reach, and retaining that pre-asymptotic late time scaling. So looking at the final results, the preferential flow and final particle exit position, we can see preferential flow in the high K gravels and sands. In figure A is the domain made transparent to see the lateral high K and size valley fill. And I've also marked a few sections on the down gradient face to show the end of the incised valley fill and prominent interconnecting sand and gravel bodies. And these outlines are on all their plots for comparison. The top row of these subplots, C through F here, are the VHGR scenarios from high to low, and they're the final position of the particle colored by the time they exit the domain. So you can see that there are lighter colors in these sand and gravel bodies, indicating a relatively faster time that they're exiting. So they're moving quicker through those bodies and preferentially flowing. And the bottom row is the same thing, except they're colored by the position that they exit the domain. So dark means on the front face and light means on the back face. And so you can see that we're getting much more transmission of particles in these horizontal flow scenarios through the preferential pathways, and they indicate preferential flow along the high K networks that terminate on this face. Here's the same transport video again, but this time I'm showing the low K paleosols. And what you should notice here is that at high VHGR, they're advection dominant, and we see mass move right through them. But as the flow is more horizontal, the paleosols are diffusion dominant, and the mud is slow advection to diffusion dominant. So it's right in that transition zone. And we see transport through the paleosol still, but much less, and only through windows in the layers, in contrast to VHGR equal to 100, where it's all advection dominant, it's just moving straight through. We also see more mass hold back in the low VHGR and preferential flow and in the percolating pathways that exit that front face. So that's the bulk of the presentation. I have 2 more slides here. On the right, I'm showing an animation of the same VHGR scenarios, but now I'm showing 20 particles per scenario and highlighting the full trajectories, and different colors just indicate different particles. The take-home message from this study is that we observe non-Fickian transport under more horizontal flow. Also, strong vertical gradients by way of transitioning low K facies from diffusion to advection dominance can reduce the tailing and preferential flow, and geology really matters. And this research, kind of tying it all together, gets us one step closer to developing upscaled models that accurately describe how contaminants move through groundwater. And this will help us better manage groundwater quality in basins worldwide. Specifically, our results underscore why the transient transport based on the ADE often fails to reproduce non-Fickian transport. When flow direction changes, this alters the governing physics of the geologic domain with consequences on non-Fickian preferential flow and tailing. The results also suggest a conceptual model of non-point source transport characterized by oscillating patterns of plume migration controlled by pumping and recharge. they suggest that the ADE might be more appropriate to model transport when the mean flow is mostly vertical, but that the ADE will fail to handle increased tailing under more horizontal flow conditions. Our plume migration simulations also indicate pumping can significantly increase the vertical migration and hence concentration of contaminants at depth. And lastly, a promising way forward towards creating accurate upscaled regional models is to first understand how diffusion and advection dominant your system is, and then, as necessary, incorporate changes in the mean flow direction and Peclet number into the mass transfer processes of the model. And with that, I end my presentation. Thanks for your time and attention.